Honestly, it's the hallway track. Like, the spaces where I've learned the most at CppCon have been in the evenings, hanging out with people over a drink or at dinner and just chatting.
Hello everyone, thank you for coming to this talk. I'm glad that you came, although I find it just a little bit strange since I would much rather like to be on these other talks where, where I listen and other people talk. But just first few words about me. I work at the University of Novi Sad, Serbia. I do teaching a lot, but besides teaching, I also have some background in industry work, in compilers and embedded systems, and in general, I try to live up to Bjarne's ideals about teaching programming and also practically doing programming. Now, this topic of session types, as you've seen, it's titled like a journey, but programmer's journey. And that's important because the session types are a mathematical term, which we will try to use in pretty practical circumstances. Of course, there usually have to be some kind of motive besides just being interesting. But in this particular case, motive was unexpectedly strong. And it was that a friend of mine told me that it cannot be done in C++. So, as the commonplace goes, people say, hold my beer, right? But it was not quite like that because I like to hold my beer while I code. Yeah, I'm a bit slower that way, but at least I know where my beer is. Because I had a lot of bad experience. I don't know if you had bad experience with leaving beer with a friend. Because I usually say to people who didn't have bad experience with that, you just didn't do it a lot and on scale, right? So it's like shared pointers and dynamic allocation. You have new beers, deleting beers, leaking problems, all that stuff. So anyway, the question was, can it be done in C++? As you will see later, it has been done in many different ways and with different levels of practical usability in many other languages. But in C++, at least I'm not aware that anyone tried. So I did try. And the idea is for you to be judges whether I managed to do this or not. Totally unrelated stuff to the fact that you're going to be judges for this. I have really nice sweets here, really cool stuff from Serbia. Just if you have opportunity to try that sometimes, do not miss it, right? But anyway, coming back to the topic, in order for you to be judges, I need to kind of explain what is the task, what are these session types, and how I'm going to implement them sort of in C++. So this will be interesting journey. I hope you will have some interesting insights together with me. Nothing revolutionary, nothing too complicated, but I think you'll like it. Anyway, the term session type, of course, has this part type. And type is one of those terms that is used a lot and has a bunch of overloaded meanings. So different meanings overlap just enough for it to be complicated to understand when are we talking about which meaning, right? But still are different enough that they don't mean the same thing. And it's not by accident that great Albert Einstein said that normal adult programmer never gives a thought about types. That's something which he has taught and learned as a child. And he, on the other hand, developed so slowly that he did not begin to wonder about types until he was an adult. And that was similar to what he was saying about space and time. He said that on a CppCast. That's the same occasion when he said, "Do not trust internet quotes." So let's start with the definition of type in a mathematical sense. And clearly, you will see that that's not going to be the path we're going to take, because that reminds me to one, let's say, older question. When I was in high school, we had a teacher who liked to ask us this from time to time to define a set. And the expected answer was, well, set is a primitive thing. Yeah, like we define other things based on sets. So it's not something that we do. We can describe a set in a sense, but trying to grasp the formal definition is a bit harder thing. Of course, now if you go into the history of type theory, we have idea to overcome Russell's paradox. You probably know about that. So in any case, that's a different way of looking at things, where type is a primitive thing, not a set, but we're not going to go down that rabbit hole. The point is that we will try to pose a question differently. So in the next step, we ask just what is a type without formal definition. But that question will also not get us too far, because the honest answer would be depends on who you ask, right? So jokingly, we can say that those are so-called dependent types, but we're not going to go down that rabbit hole either, right? So the third question that we'll ask, and I think we will get the best mileage out of it, is what are types used for in programming and in programming languages? And the next slide I added just at the conference. I was kind of inspired by the talks about Bitcoins and cryptocurrencies. And it was mentioned in one of these talks because it's very analogous, in my opinion, to money. So when we talk about money, we consider money currency that we use, but it's often very good to remind ourselves or to know that there are actually different roles that money plays. There are 3 to 4 different roles depending on the literature you are consulting, but money is used as a medium of exchange, as a store of value, and as a unit of account. So each of these 3 roles is slightly different, and then almost for engineering practical reasons, in most cases we use single currency for all 3 roles, right? But in many cases, in some of the cases, we actually tend to use something else. So most obviously for store of value, we change to some other currency or some commodity or that kind of stuff. So in that way, these are some things that types are used for. I kind of compiled that from different literature. People will mention 5, 6, or maybe even 7 things that types are used in programming. So let's go quickly through these things just to get a better idea. So one thing that types are used for is abstraction. So it's much easier when we know a type. Type gives us enough information so that we know how to work with something, and then we don't need to know all the details behind that. So that's one role the types play. Another role is documentation. I kind of extend that a bit, and I think it's pretty important role because types inform us how we should use things, how we should interact with something. And the most obvious and most popular thing that I think shows that is this completion thing. When you start with the name of your object, you add dot operator, and usually development environments will offer you what is possible to do with these objects. I like that feature a lot. I find it to be very useful. I find students who are beginners to like that a lot also. And I can tell you, I talked with several people who are mostly in functional programming, Haskell, and many other languages, and they're kind of jealous of this thing in object-oriented approach, that you can quickly see what is possible to do with an object. We will come back to that later. It will be a very important thing for the rest of the talk. Another category is efficiency. And sometimes it is explained in historical context. So the first programming languages kind of had that separation. Typical example, whether we are performing some operation on integer type, integer values, or floating point types, that will obviously influence how efficiently that is implemented under the hood. Of course, we have the same issues today. They're kind of a bit hidden because these days compilers themselves try to figure out what is actually a type of an object and use that to generate better optimizations and generate better code. Expressivity is also quite important, and we can think about two extremes, like if we consider an operation and operands, right? If operands are without any type, or they are all of one single type, whatever that might be, then all the information about what we do with those objects is coded in the operation itself. This way, we kind of separate that. Part of the information of what we are doing is encoded in the type, and part in the operation. And in C++, it's pretty obvious with the overloading of functions and operations. Detecting errors, now I deliberately kind of push this towards the end because I find that when people talk about types, this is first thing that they mention. Like, types are there to help us detect some problems in our code. So doing something wrong, usually we are thinking by accident. If we want to do something deliberately, that I think is a totally different category. In other talks, one keynote was about that on this conference. So if we do something that doesn't fit the type, it will be detected as error. And now, before we see the last role of programming types, I just want to draw your attention to the fact that whenever we talk about each of these things, there are actually, in my opinion, two directions, right? So one direction is towards the computer, towards the compiler, and compiler asks, does the code use objects according to their types, okay? But also there is another direction where we as a programmer inform ourselves how to use the objects and what's the meaning of the code based on those types and those objects. So the meaning is very important to understanding the code, and I think, that's my personal opinion, then when we talk about the types and using them for detecting errors, we sometimes tend to forget that understanding of the code is very important, because programs are not written just to be compiled and executed. They are written so that other programmers and ourselves a bit later in time read that and understand that. And the final thing is safety. So if type was overloaded with meaning, safety is also overloaded with meaning. So my definition for the purpose of this talk will again be hard to tell. There are varying explanations. Approximate explanation would be like, it's a guarantee. Now, that's an important thing, because in detecting errors, we were just saying, okay, if we can detect some errors, that's a good thing. But here we say, no, there is a guarantee that there are no certain kinds of errors, or slightly simplified, being unable to do a wrong thing. And now, as I said, with money and its roles, again, we do not achieve all of these things just by types and type systems in our language. So just a few examples. We use, obviously, different kind of documentation to convey the meaning of our code or our parts of our code. We use compilers in different modes or other kinds of static analyzers to check for certain kinds of errors. So we didn't express some of the properties within a type system, but we use a separate tool. Contracts could be viewed as another mechanism to do that. So separate than the original type system, for example, in C++ and in many other languages. But before we move forward, we need to settle with some kind of definition. And this first part is pretty easy. If you look at C++, I'll go anytime with Bjarne's definition, and that's the type-defined set of possible values and set of operations for an object. So technically, this is a type of an object, and it is not quite what is meant when we say session type, because we don't have a type of an object, but type of a session. So now we will switch to this other part of the term, session, and what it means. So it's interaction of two or more entities. It has some beginning, it has some end, and in between a sequence of some kind of interactions is happening. So we can view that as a passing of messages or whatever. It tends to be abstract. We can describe those valid expected sequences of interaction in different manners. So one of the most typical approaches with interaction diagram. So we have two entities here, proverbial client and server, and they have a simple interaction. Client is sending two ints to server, then it chooses whether it wants addition to be performed or division. So that's the model we will use for other illustrations. So server is offering kind of calculation services. And then depending on the request, it will return appropriate value. And finally, the interaction will end, this session will end. So now we can start to see the basic ideas, because this describes valid sequence of interactions. So it serves almost all the purposes that we show that type has. So we are explaining what is a proper way to interact, and we would like to have some kind of detection if we are not interacting in that particular way. It also informs us on what is expected so that we can potentially implement that. But there are other ways to express this kind of interaction. And I will just show one simple formula to illustrate that. And if you go into the mathematical aspects of session types, you will see this a lot. So in this formula, we are describing server side. So these question marks are usually used to notate that we are receiving message. This ampersand is an offer, like the server is offering the other endpoint, the other entity, to choose whether they are continue the path of addition or choose the path of division. Then server will receive int or double, that's the exclamation mark, and then finally it's the end. If you have ever seen CSP, that's communication sequential processing, if I remember correctly, that kind of reminds me on that. So really similar notation. However, this is just one side of the interaction. Usually when we have two sides of interaction, we have something called the dual formula. And as you can see, it's relatively easy. If one side is receiving two integers, the other side needs to send two integers. And again, when we have offer, we have choice operator, where in our case, client chooses which path to take. So session types, a little bit simplifying answer would be that they're formal description of messages, whatever that means, because it can be pretty abstract and depends on the context, so that it can be checked for correctness. And now again, without going too much into the rabbit hole, correctness can mean different things, so that we have a valid message format and valid message order, but also absence of deadlocks or some proof of eventual termination of the communication and other interesting properties. For just two processes, we call that binary session types. And that's the easier thing. And of course, in this talk, I will focus only on that. But much more interesting, especially from the part of verification, is something called multi-party session types, where we have more than one entity interacting, and then it's much more interesting and harder to see whether we have deadlocks and whether everything checks out. For binary types, you will see much more easier. So now we will combine these two things together. If we understand session types properly, we notice that they are actually describing a behavior. And that's also important because there is a term behavior types, which is also used a lot. This is, in my opinion, probably the biggest and best reference. So if you want to learn more about this from the mathematical point of view, this would be the place to start. So anyway, behavior is like, okay, first receive an int, no other operations are allowed. That's what is expected by the session type. Then after receiving an integer, again receive another integer, and you get the idea. So connecting that with Bjarne's types, we can say that it's like Bjarne's types, but they are changing after every operation. So something like this. We have set of allowed operations on our object, but we have this kind of diagram. Whatever we do, it will also change our type or change the set of allowed operations. So for some reason, in each of these connections, I kind of expressed the typical, the simple function call and also member function call, because those are two approaches that we can take. We will see that later. Now, this is not so strange and surprising proposition. In reality, we have already something like that. It's just not that obvious. So here we have something that we can arguably say, okay, but that's not an object yet, right? But that's the initial state when we are about to create our object. So we can create it, which can construct it in various different ways. Once we actually do construct it, we have this main set 0, which is a typical set of allowed operations, and any other operations keeps us in that set. But if we perform destructor call, it will change the state, because after that we can just free the memory and nothing else. But maybe some of you already noticed it's even more complicated since C++11, because we also have a move thing. So if we do a move, we actually have a totally different set of allowed operations. When we move out of object, we can either destroy it, so that's the bottom line, or we can, with assignment operator, give it a new value, and then we go back into the initial set. By the way, this kind of diagram is and these nodes are sometimes called type states. So there is a branch of research that models this as a kind of type states, and the purpose is to detect uninitialized variables and different kinds of properties like that. So instead of what we have right now, we would like to have something like this. So each time we perform something, we change the valid operation set, and at the end we have a destruction, which it could be equivalent to closure of the connection. So before we see some code, we have to answer a few more questions. So I already told you that session types are used already in many other programming languages in varying level of support and practical usage. But we can identify 3 different approaches in how the session types are used. So I would say the most typical approach goes something like this. So we first describe our protocol in more or less abstract terms. So we do not start working in any programming language. So we have a protocol description. Then we write and verify that protocol. There is a tool used by part of the community that works on session types called Scribble. So I just flashed here one example. This is how they describe protocols, so they can use the tool to verify that there are certain properties satisfied for that protocol. But for our approach here, it's important to see that they start with protocol, they verify it, and they use additional tools to generate code for the particular language. So one thing that I was able to play with, generate code for Java. So it will generate classes and everything, and then you can use that code in your code that actually performs message passing and everything. Another approach is actually totally reverse. It's a little bit rarer, but it also has some benefits. So we just write our code. We don't care about protocol. We express directly what we want. Of course, we would need to abide by certain rules. How do we express actually the transfer of messages and everything? And then we have 2 slightly different paths. Either we have a separate tool that will extract that information from our code and say, okay, this is the actual protocol, and now we can check it and verify it. Or even in some languages, and I must say I always find that really akin to kind of magic, that type can be actually inferred. So in C++, we don't have a lot of ability to do that, but in some languages that is actually possible. So then we actually get the language type, the type expressed in that programming language, and then from that we can extract protocol description. But the third approach is what we will use here, and I think it's the most natural approach for C++. We start from the middle. So we use language facilities to describe our protocol, our session type, and then we have 2 steps. One is use that type to write the actual code that performs communication. And also we can, from that language type, extract protocol description and then separately, maybe as a step in build process, run our tool and check whether our protocol is satisfied. But in this talk, we will just focus on this bottom part for 2 reasons. One is just constraint in time, and of course I didn't do the upper part, and finally because we are focusing just on binary session types, this part with verification of the protocol is not super important. Just adhering to what we expressed in language types is pretty decent. So let's try to implement that a bit, and as you know, there's nothing scarier than empty source file. And again, there are a bunch of decisions that needs to be made, a bunch of design decisions that often have a long lasting consequences, right? And it's hard to figure out what to do. So again, we have different approaches and different choices that we have to make. So one obvious approach to implement this would be to go with functional style. And that's pretty natural because if you know functional programming, we basically use objects and create the new ones. There is no mutation, right? So the idea of, okay, we have something of a certain type, we do something with it, and we get something new of a different type, and we continue using that, that's pretty natural there, right? So that would be a preferred choice from that perspective. But I didn't take that road, okay? Of course, in that path, we also have different ideas, either use monads or continuation passing or whatever. Again, not going down that rabbit hole. Why? For various reasons, but again, you see this thingy with the dot. I find that to be really cool and really convenient, so I wanted to use that as much as possible. So we will see how that goes. And also another design decision needs to be made. We didn't talk about the external communication, how it is performed. And if you look carefully about session types, which are pretty abstract, they abstract it as some kind of channels. So we have a channel, whatever that means, and that's the way we communicate. The endpoints are communicating between each others. If we kind of unpack that, there are usually two ways this is described. Either we have a named channels, and then we assign purpose to those channels for what kind of communication they are used, or we use abstraction called actors, where basically each actor has its own channel. So we are saying, okay, I'm talking to this actor, which basically means I'm sending to its channel. An actor is reading only from its own channel. But that's the abstract level. The practical level is how we're going to actually perform communication. And roughly, we can see two broad cases. Either we are communicating between processes or threads or coroutines or something. So we would use some kind of concurrent queues in that case. There are a bunch of different queues: bounded, unbounded, synchronous, asynchronous, single consumer, multiple producers, etc., etc. But we're not going to go down that rabbit hole either. Then in other case, we are communicating through networking sockets. And then again, if we want to do that, practically a lot of stuff to think about. And again, we will not go down that rabbit hole either. So for the purpose of this talk, we will do some pretty high-level abstraction and go for very simple queue that supports send and receive. And that's it. That will be enough for illustration of this. Under the hood, that queue supports multiple producers and multiple consumers, because that was the code that I could easily find and use, but we don't need that. We actually have a single consumer and single producer. Now, coming back to this question, channels of actors, we really need to make a decision whether we are going to use a channel approach or actors approach. And the practical difference is explained below. So if we have a channel and say, okay, between the two endpoints, channel is used for communication, then that channel needs to be a full duplex. So one side can write to channel and read from the same channel, and the other side do that as well. However, if we take the actors approach, we will have two channels. Each side will have its own channel. So we will choose the latter approach, the approach with actors. By the way, this idea of channels versus actors, intuitively, I think it's noticeable that you can change from one approach to another. So they are actually equivalent. But interestingly enough, there is a paper that kind of proves that. So you can always go from actors to channels and from channels to actors, so in case you are wondering. So here is just one quick slide of our abstraction. Very simple. I only later thought that maybe I should have gone fully with the Rust's approach. I don't know if you've seen, I actually saw that on some of the other talks related to C++ and on some other conferences, that it has these channels. So it generates separate the send object and receive object for each channel. But I'm combining them here. So we have this com thing that has a send and a receive. As you see at the bottom of the slide, we will actually have two queues, two channels, and we will reverse them. So the upper object is for one endpoint and the other object is for other endpoint, and that's how they will communicate. Also observe the send and receive, how it's done, because we will change the types of messages that we send. The queue itself, the channel, is abstract enough that it accepts any type of message, but here we explicitly send a particular type and we explicitly receive a particular type. Now let's see this in usage. In the bottom left part, you see the interaction diagram. In the upper right part, you see the same thing expressed in this formula. But in the other parts of the slide, you have the code that is using this channel to communicate. Now this code, we still don't have any notion of session types. We simply use this channel to communicate. And this is how we would do it. So you see that we are using receive to explicitly say what are we going to receive, what type of value. We send, in this case, addition of these two values. We explicitly close our channel, and on the receiving end, on the client side, we send two integers. We receive the integer as a result, and we have some additional code. In this case, it's interaction with the user, but it can be anything else. I'm highlighting just the communication part of the code. Now, obviously, if you look at this, you can, I guess, quickly see what can go wrong with this code. Almost any error that we make in our code and doesn't fit with the expected message interaction will not be detected by the compiler and cause a serious problem in execution. So if we missed one of these sends or receives, or instead of receiving, we want to send, then we have again a deadlock, or we make the wrong type of the message we are sending or receiving. All of that is simply undetected. So if we want to change a protocol, so let's say that we don't want to do addition anymore, but we want to do division, and that's a very simple example just to force me to change the type of the returning value. So if we want to do division, we want to have result as a double. So we propagate the changes, right? But of course, we didn't do the change on the bottom right part, and that will fail spectacularly and no way for you to know. So the only way is to actually consult your documentation and everything. So now let's see a bit of implementation. I will not go into too much detail, and in reality, it's pretty simple. There is a lot of room to make it even better and more shinier. So the idea is that we introduce these types. So for sending, receiving, offer, and choice. We already saw that in our formulas. And in the bottom part, you see how we will express that inside the C++. We will say, okay, receive one int, send one int, and then quit. That's the end of our session. That's the server part. If we want the client part, we have to do the opposite thing, right? But again, if we have to write manually the client versions and the server's version and client version, we can create error there. So that's why we will add this dual thing. So we just express for one side and we get easily the type for the other side, so-called dual type. So that way we escape some errors. Again, few possible design choices in implementation, and I promise these are the last. This is the last set of choices. is, okay, we expressed in the previous slide something that we will call protocol. That's the session type essentially. And we have this communication thingy, communication channel. So how we connect these two. So we have three approaches here that separate them. So we have a communication channel as one thing and protocol as the other thing. But each of these approaches have several issues with them. So one approach, we strike it down because we don't have this thing with point and then suggestion of member functions. The other two approaches are either too difficult to implement, a lot of template things needs to be done, or we can easily by accident access the channel and therefore do something with it, of course unintentionally, without the control of the protocol. So we will go with this approach where we will combine in channel both our protocol or session type and the communication. So let's see this simple protocol that we already seen. On the left-hand side, we have so-called manual without any support of types. And on the right-hand side, we can see how to do that using session types that they are implemented here. So I will have several pictures just to show you how it looks like when you use it. And I think it's quite interesting. So you start with the channel, and as you can clearly see, we specify what is the protocol. We push the dot, and it immediately says, okay, you have to receive, right? Nothing else to do. And you do the receiving thing, of course. You have to go back and actually get the result, and you notice the most problematic from the syntactic point of view thing that you need to create a new channel, which you always have to name. So I'm using stupid names like C1, C2, and that kind of stuff. So you see, I got the C1, but V1 is actually my result. And it is of type int because I expressed that inside my session type. Now again, I have another receive, okay, and I get the C2. Now I only have send as option, right? So I do what I have to do, and here I can maybe skip one additional naming and just say, okay, now I'm gonna close, and that's it. Client side will look like this, very similar. Again, everything is expressed by our types. So let's just test this and change a thing in our protocol. So instead of sending int, we will now send back double. So we are changing again from addition to division. And the left-hand side, which is done manually without the support of types, will immediately fail, and again, without any problems in compiling. But the right-hand side will just keep working because the fact that we change the type of the result will perfectly propagate in our code, and the code will continue to work as expected. Now we just have a few more additions. To this, we haven't shown usage of offer and choice. So we will now have this offer of either go with division or addition, and choice. Server function would look like this. So notice here that we have this offer function member. We will get offer, which is essentially like variant underneath. And we check which of the offers are chosen because we are rating the choice from the other side, what path they chosen. So if it's 0, then we take 0, and then we can do receive, and send. In other case, we take 1, again, receive, and send. On the client side, we are choosing. So when we get this channel, we immediately choose, and only 2 member functions are offered, select 0 or select 1, and depending on which one we choose, the appropriate information will be sent to the other side, and again we will get the appropriate type. So C1 in this branch will express that path, the C1 in another branch will express the other path. And the final addition to this is actually to perform a loop. So far, we will have just one path, and we follow it till the end, but we can also express loops, and we will complicate our type by saying, okay, we can do this as much as we want. So we choose either addition or division. When it is performed, we again say whether you want to quit or do you want to do it again. Now that we have all that, we can see one more thing, and that's the last thing from the implementation side, how the actual channels are implemented. There are a few details here. Of course, you see that communication type, mcom, that's the part that we do send and receive through. Otherwise, we see how this change of types is actually performed. Nothing too important and probably not easy to read while while you're listening to this talk, but I'll send you slides and you can, if you want, check it in more detail. But I will show you one important thing, and that's this move. So every time we actually return an object, we are moving from this, and we will see why that is important. Of course, this is how we implement choose and offer, and this is how we implement loop. And you notice this CTX, that's context, that's that's important only for loops. Without loops, we do not need that context. So finally, we can actually implement that. And one thing to note is with this enter, we say, okay, we are starting the loop, right? And the expected pattern is to have while true, and we exit on break. Some people might say it's a bit ugly, but it works pretty well. And as you can see in this branch where we say, oh, we want to repeat, you see what we do. We have only this member function loop, and we get again object of the same type as this C1 thing. So now we can tie that with all this moving, because here, when we did something with C1, right, we moved from that object. So afterwards, only valid things to do is either destroy it or assign new value to it. And we assign new value to it. So it's a valid thing. On the other hand, we have the client function. And if you look carefully, we have an error here. But it's a different kind of error. We are not making error in the wrong action or the wrong type. We actually cannot do that, right? But we accessed C1 again after it was moved from. So you see, we performed the send. The new object we should work on is actually C2, but by accident, we used C1. And that's the interesting thing, because as far as I could play with it, Clang Tidy pretty effectively detects this. So we can say that it's also pretty type safe. And finally, let's see the overhead this introduced, because of course in C++ we are quite interested in efficiency, and whenever we do something a little bit more complicated with templates, it's often useful to see how much overhead that added. So I did a comparison between manual usage of my communication abstraction and the explicit usage of session types. And you can see the results. I only tested with Clang 19 for PC architecture. So in total, the change is not very big, just 6%. But if we focus on client and server function, we see that client function, the difference is just 6.8%. And server function, the difference is much bigger. It's, I think, obvious why that difference is so big for server and not so big for client. And that's because in client, we had a lot of code that actually interacts with the user. So we have writing to standard output, reading, and that kind of stuff, whereas server is pretty much just about communication. So unfortunately, it's a big overhead. But of course, this is just initial implementation, initial idea. There's a lot of things that can be done with it. Of course, we can improve implementation in several ways. We can have a nicer type session expression because, as you see, we have all those angle brackets. So if it tends to be complicated, it's a bit harder. We can work on that. Also, I didn't not mention any connection dropping in this talk, and that's something that's not pretty nicely expressed in these session types. Of course, the upper part of the picture you maybe remember from the earlier. So can we extract description of the protocol in this Scribble code and then use that tool to perform verification? And that will be much more interesting if we are to implement multi-party session types. But of course, if you think about multi-party session types, it pretty much complicates the way we are going to express them. But it can be done in some other languages. They did it, and I think those lessons can be used to express that in our language, in C++. And finally, let us check how all this fares comparing to what is the purpose of types. So we do have abstraction. I think it's obvious. Documentation part, I'm most proud on that one. The thing with dot is really convenient and really makes you write correct code from the start. Efficiency, you saw it, it's not so much. Expressivity, I think it's pretty good, although if you look very careful, we cannot have nested loops. So that's one part of expressivity that we need to work on. Detecting errors, pretty good at it. And safety part, as I said, it's kind of difficult how you interpret it, and I wouldn't be so sure to give any guarantees about it, but for sure it's much better than what we had previously. So anyway, coming back to the end of the talk, I don't know if you remembered what your role is. This is very tasty just saying. So I hope this will not be the answer. And please just the way you can express to me whether you reach the verdict that it is an implementation of session types in C++ or not. So if you think it is, just give me applause. Thank you. Now we have some time for questions, but don't forget that after questions, I really do have this here and you're free to take it.
So I don't know if it's just me, but I can't help but see the analogy between your set of operations and state machines. Is it like a compile-time, compiler-validated state machine implementation?
Yes, you are perfectly right. And I talked with a few people during the conference, and some of them showed them their implementation, different implementations of state machines. And I think you're pretty right. It's pretty analogous. Of course, this has advantage of being compile time verified. So in a sense, if you have a strong need for state machine, right? Maybe those other ways to express them have much more benefits. So the efficiency, a lot of different state changes and that kind of stuff, right? But if you are focusing just on some communication things, then this might be a way to go.
Thank you for the talk. I lost a little bit in the point of asynchronous and synchronous operations because it seems pretty synchronous one. So can you elaborate on this?
Yes, yes. Well, the part about synchronous and asynchronous is kind of embedded in the communication part. So technically, the sending is not blocking, but receiving is blocking here. And if you have just two parties that communicate, it's not such a big deal. But if you have more parties involved in communication, then whether it's synchronous or asynchronous is important, but that kind of goes into this upper part. When we express that in this scribble and in this protocol, we can verify that it will be still valid if it's asynchronous. So that's...
Thank you for the talk. I really enjoyed the academic approach that you took. So I could not help but wonder that during the 47th slide where you explained different approaches, how can we implement, do you think that when C++ reflections come to the C++ 26 could help us to make the implementation more easier and more affordable for us?
You mean this slide?
Exactly.
Yes. Yes, you're right. And to be honest, I knew that reflections are coming, but until the conference, I almost didn't pay any attention to that. For sure, the way I see it, and I think many people agree, at least what I saw in the talks, reflections, especially the generative part, will kind of replace templates in many cases. So this would be, I guess, one of the usages where reflection can replace them, but I'm not quite sure at the moment.
Thank you.
Hi, great talk. Yeah, I can't help but see the comparison or similarities with senders and receivers, the proposal that's going into the working draft. And maybe one way that I think of it, please correct me if I'm wrong, is that with your approach, you describe the protocol first, and then you use it in very normal looking C++ code, like old style, normal C++. And when you use senders and receivers, you're writing code in a domain-specific callback kind of language, and then the protocol is a product of, or a side effect of the thing that you produced. And so I can see a couple advantages of your approach, not that they're competing, but
Yeah.
that first, that you can see the protocol in code, like you've described it as a type and it's transparent. And the second approach is that it's natural to construct the dual. But one of the things I noticed with your approach is that there's a bit of maybe a mismatch between the branch, the offer or choice as described in the type and as described in the code, which leads to potential for errors. Like, because you have to notice, oh, did I take A, B, or C? And if this, then I have to do something to get to A, B, or C, versus with a callback approach, that would just like fall out of the protocol. So I just wanted to see if you had any comments about that.
Your comment is simply on the spot. You're right. I agree, and I wanted to think about senders and receivers, but to be honest, I still didn't grasp the whole idea from the standard. But also you notice what is the weakest point in this approach, and that's offer and choice. That's where the errors can be made. And of course, I appreciate and understand your last comment. That's for sure something that can work, and I will look into that. Thank you.
As I watched you lay out, I didn't have any idea what a session type even was until I came to this talk. But I have designed protocols before, and it reminded me very much of what I did for one of my very first protocol designs, because having the very explicit state machines about who expects what when makes it very easy to detect when you've created a protocol in which one side doesn't have a clear idea of what the state of the other side is and what it should be expecting at that point in time. And so I think regardless of whether you can actually encode it directly in C++, going through the exercise of creating these session types to describe your protocol is very useful. And it's kind of neat that you can actually describe it in C++ in this way.
Yeah, I agree. I like you understand my idea and you got the vibe. So, okay, thank you for questions and don't forget. Thank you.